So this is a video about ionic compounds and metals, and we're going to kind of do sidetrack a little bit and talk about naming compounds and all compounds. This is important because we are definitely going to be using this the rest of the school year. And this will be a little short that you can come back and hit if you want to review identifying compounds and naming them. So one of the things that we need to be able to do is, if we look at the Chapter 7 PowerPoint A, we're going to use part of that for this, this video short, and that would be dot diagrams. Dot diagrams are the representation or a picture, a snapshot that tells us the valence shell electrons. It's an important term to know. The valence shell electrons are the outer shell. And you know, they say you can't judge a book by its cover. Well, you can kind of judge an atom by its cover. The outer shell tells the way it's going to react. And it's really easy for the A elements to do dot diagrams. Look at the Roman numerals up at the top, and you see 1, 2, 3, 4, 5, 6, 7, and then 0, which is also called 8A. The number of the Roman numeral tells you the number of dots for the dot diagram. So you should look at these real quickly, and it's one of the easiest things you'll do in this chapter is doing dot diagrams. But it's important too because it also tells us a lot about the way that the atom is going to combine with other elements. So the dot diagrams, look over this chart. I think that's an important thing. Another thing that you'll want to do is you want to be able to determine when an atom becomes an ion, what the charges are. So we have these monatomic ions that have one charge. So the A elements, for the most part, all of the A elements have one charge. And this is really easy because in about 2 minutes you could know about 20 of these ions. So first of all, any Roman numeral 1, 2, or 3, whether it be 1A, 2A, 3A, or 1B, 2B, 3B, those are almost always going to be that Roman numeral positive because those are metals, and metals are just very, very few exceptions. They are always positive. For you, they'll always be positive. So that gives you already, you know, when you look at the periodic table, you can see already that you know, you have 1A, 2A, 3A, and then you also have 1B, 2B, and 3B. So that's just about 20 elements right there. Now, what does that mean? Well, one thing that you need to know is that atoms are always neutral when they're atoms. The word atom tells you it's neutral. When it becomes charged, we call it an ion. Easy way to remember that would be to think of the light switch. I on, I off. It deals with electricity, right? The light deals with electricity. So ions are when an atom gains or loses electrons. And when it gains or loses electrons, it has a charge, and we call it an ion. When it's a positive ion, we call it a cation. And when it's a negative ion, we call it an anion. And that's kind of easy because the cation has this T in it, so that T looks a lot like a plus. So if we cover up the Ca, it looks like positive ion. So that'll help you remember that. Now, why is it that we're knowing these charges? Why is it important? Because when we talk about an ionic compound, we have this little divider line over here that starts between boron and aluminum, goes over, down, over, down, over, down, over, down, ends up down here between polonium and actinium. And it is the stair step that separates the metals and the nonmetals. So it's important to know where that is because up here are the nonmetals and down here are the metals. You don't have to memorize it. Look up here, it's oxygen. You know oxygen's not a metal. That's a nonmetal. Sulfur, nitrogen, so those are the nonmetals. Down here, things like copper and zinc, you recognize those. Iron, they're all the metals. So when we want to identify types of compounds, it's really important that we figure out, is it ionic? And that means that we have, easy way to remember that is ion both sides, ionic. In other words, if I have a metal and a non-metal, one from each side, then it's ionic. If they're both from above the stair step up here, then it's molecular. So identifying compounds, that would be a good general rule. Now there are some other ways and some more specific rules, but for now that's going to be a good general rule that we'll use until we get to those other rules. So you need to know, is it ionic? Is it molecular? Good way to know is to look at the first capital letter, and if that's a metal, then if it's a compound and that's a metal, then it's going to be ionic. So you know right away it's ionic compound. If the first capital letter, the first element symbol is a nonmetal, well, then it's probably two nonmetals. That's a good clue. And the number of capital letters tells you how many different types of elements there are in the compound. So when we think of monatomic ions, already the ones with one charge, you know a big chunk of them. You know a lot of them. Now we're going to be talking also about representative particles. An atom is the representative particle of an element. In other words, if we got down to the very simplest part of an element that still acted, smelled like, looked like the element, that would be the atom, and it's still that element. But if we break it into little pieces of protons, neutrons, electrons, it's no longer that element. So the atom is the representative particle for most elements. The molecule is the representative particle for molecular compounds. That's with two nonmetals. And formula unit would be the one for ionic, ion both sides, for ionic compounds. You should know those three types of representative particles. That's what we're going to be counting when we count particles. All right, so element charges. So you've got this chart. If you look at this, you see right away that it's actually fairly easy. These are zero charge. Noble gases don't make a charge. 0, -1, -2, -3, plus or minus 4, and that's where we shift from minus to plus. Then we go +3, +2, +1. So if you look at that, that's probably close to 30 elements that you know the charges of. Now what does that mean? Well, that means that as atoms they're neutral, but when they become stable, and that's why they lose or gain electrons to be more stable, they get a charge. And when they get a charge, that is one of the reasons why ionic compounds come together. It's the main reason, because a plus and a minus attract, and when one loses electrons and one gains electrons, they attract to each other. And that would be how we get ionic compounds. So you're going to need to be able to write formulas and name ionic compounds. There are a lot of practice pages, and what I recommend is you do as many of those as you can and go through and try to write the formulas for the ones with the names, and write the names for the one with the formula. Actually, saying the name is very easy. You just say the first part and the second part. And if it's two capital letters, it always ends in "ide." If it has more than two capital letters, then chances are it's going to end in "ite" or "ate," and that has to do with the fact that it has a polyatomic ion in the second slot. You'll see that polyatomic ion chart later today. So, how is it that these come together? Well, again, everything on that side becomes positive because it loses electrons. Minus a minus is plus, just like in math. And everything up here becomes minus. They all want to be like the noble gases. Now, there are some exceptions, but for now, we're just going to talk about the ones that like to be like the noble gases. These guys are one electron away. What are they going to do in order to be like the guys next door? They're going to gain one. So 1 will gain 1 and become 2 electrons. Fluorine that has 9 will gain 1 to be like neon. Chlorine gains 1 to be like argon, and they always try to be like the closest noble gas. So you know how many they're going to gain, and when they gain those electrons, that gives them their charge. So all of these guys are closer to gain. Those guys are closer to lose. How do you know if it's closer to lose or to gain? Well, look at the number in the upper right, the whole number, and on the top, and that number, whatever it's closest to, noble gas, the closest one tells you how it's going to go. 8 is closest to 10. So it's going to gain 2 to become like 10. Now, that means it's still oxygen because it still has the 8 protons, but it gains 2 electrons, so it's got 2 more electrons than protons, and it's minus 2. It's the balance of pluses and minuses that decide. And if you gain 2 electrons, you're going to be minus 2. This whole column above the stair step is negative 2. This whole column above the stair step, minus 3. This whole column above the stair step is minus 1. So you know right away the charges of these. Now, why do we need to know these charges? Well, when they combine so that the charges neutralize. So if I had Al with a 3 plus and Cl with a 1 minus, well, I'm going to need 3 1 minuses to neutralize the 3 plus. So that means there's going to be AlCl3. Now, another way we could do this is to take this number here and that number there, and then reduce if you can, and that's called the crisscross method. This is how you write ionic formulas. AlCl3 would be the correct ionic formula, and the name would be aluminum chloride. Remember, 2 capital letters always ends in I. There's very few exceptions to that. So we've got aluminum chloride. We'll do a couple others, and you know, there's on that list, you've got a whole bunch of practice problems that you could try on that list, and I recommend that you do some of those. So let's say we've got Al, we'll do one a little more complicated, ALO. Oxygen is 2 columns over. See, it's got a minus 2. Aluminum's got a plus 3. So if we're going to do the crisscross, we take the 2 here and the 3 there, and then we get rid of these because it's no longer charged. It's now neutral, and that would be aluminum oxide. No prefixes, because ionic compounds, we crisscross, and it's only one way that it could work, so there is no confusion. Aluminum oxide is the only aluminum oxide. So that is how you write formulas, and it's also how you name them. Now, there is another list, and we call that Cops and the Mercury list in my classes because I asked them to memorize that early in the year, but there is a list that you have on your possibly useful page, and I've given all of you a possibly useful page, but if you look on landerson.net and look up monatomic ions with more than one charge, those are the ones that have more than one charge. Copper, mercury, lead, tin, and then the block, which is on the periodic table, and I will surround that block so you can see it. So these 4 are the block, and you can see that those 4 are all plus 2 and plus 3. Now the way that we memorize that, because I try to teach my students to memorize smart, not memorize long, because we put this up in this way to not really a rhyme, it's like a ditty, that chart that would probably take somebody an hour to learn, in 5 minutes they know it. And that is that cops in the mercury, lead, tin blocks. So what does all that mean? Well, the cops, like the policeman, in the mercury, mercury's a car, lead, and of course it's not L-E-D, it's L-E-A-D, lead, the element, tin, not T-E-N, but T-I-N, and then block, and the block here. So what does all that mean? Well, copper and mercury are plus 1 and plus 2, and lead and tin are double that because they're the second part, which is 2 and 4. And then all these guys inside the red box, the block, they are plus 2 and plus 3. So there you go. If you remember copper and mercury, lead, tin, block, you remember where the block is, you know that whole list already. Why is that important? Because when we say those names, you have to use Roman numerals. And it's kind of like you go to Joe Smith's house, and he's got a son named Joe, and he's got a father named Joe. Well, you know, that's confusing. So you got Joe Smith Sr., Joe Smith Jr., maybe Joe Smith III. It's the same thing. When we have copper that can be plus 1 and copper that can be plus 2, you have to say which one you're using. So if we had CuCl2 or CuCl1, and we put the 1, it's understood. You really don't have to put it. Then how do we know if we have copper 2 or copper 1? Well, you uncrisscross, and that goes back up here, and the 1 goes back up here. Here it's 1 and 1, so we know we have copper 1 in that one and copper 2 here. This would be copper 2 chloride, and the bottom one would be copper 1 chloride. There's a difference in the formula, and that's why we use the Roman numerals. So that's a big chunk of the naming. The other end of this would be the naming for the molecular compounds, and just a real quick run on that is the main difference. Again, if you have two elements, it's going to end in IDE or IDE, but you have to use prefixes. So like this is where you have carbon monoxide and carbon dioxide, because there's more than one carbon oxide. You don't crisscross. So for ionic, you crisscross. Okay, ion both sides, ionic. Crisscross to write the formulas. Never use prefixes. So you don't have to use prefixes. On molecular, you always use prefixes. So you remember carbon dioxide, that's very common. Carbon monoxide, whenever you have two nonmetals, you have to use the prefixes. And it's okay if the first prefix is mono if you leave it off. Otherwise, you could say monocarbon dioxide. That's not incorrect, but it's not the way we usually say it. But the second prefix always has to have whatever, like carbon monoxide, even though it's mono, you have to say it. So those are the naming schemes for molecular and ionic, and they're also how you write those formulas. The only other thing we have left is that if you have more than two capital letters, then you need to look at the polyatomic ion chart. And I have a copy of that on the website. You also have a copy on your possibly useful pages that you've gotten. And they are the ions that have more than one capital letter. So like phosphate and sulfate. And my groups early in the year, they memorize those so that you know them later in the year. Now I give them the charts. They don't really, most of them don't look at the charts because they know them. It would be important to know how to use those. And the only real difference, you still use the crisscross when you write them. It's just you put parentheses around the polyatomic ion, kind of like grouping like you do in math. So that would be another, another day, another time, because I wanted to try to keep this fairly short. And this is how you name compounds. So and name compounds and write formulas. So you could watch this again if you need to. Should get some of the practice problems out. There's several of those practice pages. See if you can go through those and write most of the formulas and write most of the names. Be able to identify the kind of the objectives of today, or be able to identify if you've got molecular or ionic. Remember, ion both sides, ionic. Molecular, they're both from the nonmetals. If you have an ionic, you're going to crisscross to write the formula. For molecular, you use prefixes to tell the numbers instead. So, listen to this again if you need to. Look over the charges. They're very easy. 0, -1, -2, -3, plus or minus 4, plus 3, plus 2, plus 1. You could learn that in a minute or two. It's a pattern that's easy to remember. So if you learn those charges, then you'll know how the elements go together. Try as many of those practice problems as you can, and come in for tutorials when you need to. Good luck.